Good morning, students. So, as you know, in the last class we have started the chapter Magnetostatics, and there we have discussed some basic concept and very most important, the basic law of magnetostatics. Biot-Savart's law also we have discussed. So, in today's class, I am going through some important derivations. Okay, so three derivations are there, where in each derivation we are finding the magnetic field or the magnetic induction B with respect to different cases. So in the first thing we are going magnetic field at a point. Magnetic field at a point due to a straight conductor carrying current. So this is a case of a straight conductor in which current is flowing. So in that conductor, in that straight current carrying conductor, we are finding the magnetic field B, and we are going to prove the value for B by doing a derivation. Okay, after that, magnetic field at a point along the axis of a circular coil carrying current. Here we have used straight conductor carrying current in the first derivation. So here in a circular coil in which current is moving, there we are finding the value for B. And at the last, magnetic field at a point along the axis of a solenoid. So okay, what is this solenoid? Is means it is just one electromagnet, like if one wire is there with a different number of n number of turns. So this is a wire. So in this wire, if we pass the current, if we pass the current in this wire, what happens? Current starts moving in the wire. So this will create the magnetic field. Understood? So this is used to generate the electric field by using the magnetic field by using the electric field. Okay, so this is one type of electromagnet, solenoid. Okay, so in the third derivation we are finding the magnetic field at a point along the axis of a solenoid. Okay, so let's go with the first derivation. So what is that? Magnetic field at a point due to a straight conductor carrying current. So as you know, the definition itself indicates we have to consider a straight current carrying conductor. Okay, so consider a straight conductor first. Okay, so here I'll consider a straight conductor X, Y. Okay, what is XY? XY is one straight conductor carrying current. Okay, so in this conductor, current I is flowing in the direction Y to X. Okay, then somewhere here I'll consider one point P. You can also consider these basic things with respect to the Biot-Savart's law also. There also we done the same thing. Okay, so P is a point at a distance A from the conductor. Okay, so P is located at a distance A from the conductor. A from the conductor. Okay, then consider one element AB here. So as we considered in the Biot-Savart's law. Okay, there also I considered one current element. Na? So here consider that AB is a current element. AB. Let's consider AB is a current element of length dl. AB is a current element of length dl. Okay, then we can draw a line over here from B to P. So I have drawn one line from B to P. So let's consider this length BP. The length BP, to that we'll give a value R, small r. Okay, and here this is the center point O. So from the triangle OBP, OBP is one right angle triangle, no? So consider this angle as theta. So OBP is what? Theta. Understood? So now in this condition, what we have to write? Magnetic field at a point P due to the current element AB. So, okay, so this we can write by using the Biot-Savart's law, right? So let's write the magnetic field at a point P due to the current element AB, and that magnetic field is nothing but what, you know, dB. Okay, so what that value gets as mu naught by 4 pi I dl sine theta divided by r square. How I have written this? By using the Biot-Savart's law. Who have heard the last class, they can understand. Let's call this as the equation number 1. Okay, so now as you have joined BP, let's join AP also. Okay, let's join A and P also. Okay, so then what I will do, from the point B, let draw one line. So call it as C. Okay, let's draw one line BC which is perpendicular to PA. Okay, so let's draw this BC perpendicular to the line PA. Okay, then also there also we are getting some triangles. What are those? Okay, so here we are getting the triangle OOPB. OPB is also one triangle. Okay, try to understand. OPB is a triangle, and here the angle OPB, to that I call it as a pi. So I'll write here. Okay, angle OPB is what? Pi. Same angle BPA. BPA is also an angle. To that I call it as a d pi. BPA. To that I call it as a d pi. See here, I am noting it with the red ink. Okay, see here. The angle BPA. Okay, so let's draw it like this. So this is what? This angle is what? D pi. Okay, na? So, and then, so this, try to understand, this angle OBP is theta, OPB is pi, and BPA is d pi. Okay, then in this triangle, B, C and P, can you write what is the angle of value for BC in the triangle BCP? Okay, BCP. Can you write the value? Why? Because here we are having the value d pi. Okay, d pi is the theta value, angle. Okay, so if you apply the sine theta over here, sine theta, so can you write the value BC as BC equal to, can you write dl sine theta? BC equal to dl sine theta, and BC equal to r d pi. Okay, so these are the values we got from the diagram. Okay, so now can you write the equation 1? Can you write the equation 1 as mu naught upon 4 pi? Okay, I dl sine theta value we have written r d pi. Okay, divided by r square. Right? So the same thing, can you write it as mu naught by 4 pi and I d pi divided by r. Okay, na? So now in the triangle OPB, OPB. So go on writing all those things. Write the heading, first derivation, considering all these things. Go on writing the derivation by yourself. Okay. So in the triangle, consider the triangle OPB. Consider the triangle OPB. Can you write the value for cos pi? Can you write? Yes, that is cos pi equal to A divided by R. This is A and R is VP is nothing but R. Okay, A by R, and hence R is equal to what? A. R is equal to A divided by cos pi. So can you write the value of dB now? dB equal to mu naught upon 4 pi I as it is. So this R value we have to substitute there. Okay, R is equal to A by cos pi. So cos pi I'll take it in the numerator, cos pi d pi divided by A. Okay, let's call this as equation number 2. Okay, so now see here, we are finding the magnetic field in this situation, no? So how the direction of magnetic field dB will be? Sorry, this is not visible. Okay, so here what I have written, just R value and substituting R value here, and I have written the equation number 2. Okay, so here the direction of dB, the direction of the differential magnetic field will be perpendicular. Perpendicular to what? The plane containing this length element and the distance R. Means what? Consider this page is there. On this page current element is there, means the magnetic field direction will be like this, perpendicular. Understood? So where the current element, so in this, on this paper, if the current element is there, current element dl is there, okay, and up to here the p is there, okay na. Let's just consider, so r is the distance between these two. So on this paper the current element and r are existing, no? So to this current element the magnetic field is perpendicular in this direction. Understood? So the direction of the dB will be what? Perpendicular to the plane containing dl and r. So it will be, so let consider again two angles. Again two angles. Pi 1 and pi 2. Where means these two angles are made by the ends of the wire. Ends of the wire means what? X and Y. Okay. So this X and Y, if you draw the line like this, PY, and if you draw the line XP, so at that time also you are getting two angles, right? So let's draw those lines first. Y to P. Y to P you draw one line, and again from X to P you draw one line. Okay, you write it properly. Okay, so X and Y. So this angle is pi 1, where the line joining Y and P is making an angle pi with the center line. Okay, and the same thing from this central line to this line, whatever the angle is there, no, this angle, that I call it as the pi 2. Means if you join the end points of that wire to point P, they are making an angle pi 1 and pi 2 with the point P. Then you have to consider the magnetic field due to the whole conductor. So here whatever the magnetic field you have written, that is only for this current element. Only here you have found this magnetic field. Okay, so to whole conductor you have to find the magnetic field now. So that's why I am taking the angles pi 1 and pi 2. So at that time, how can we write the magnetic field? So dB is what? Magnetic field with respect to dl only. So we are considering the whole conductor now. Means what should be our magnetic field? That is B. Okay, so that is B. Magnetic field is B. Okay, so here what you can write, integration from pi 1 to pi 2, right? Integration from pi 1 to pi 2 whole conductor. Okay, that is mu naught upon 4 pi, whatever the value we are having here, mu naught upon 4 pi and I cos pi d pi divided by a. Okay, so this is the value. So can you write it now? Mu naught upon 4 pi, and one more thing, this pi 1 angle I am taking it as minus pi 1, minus pi 1 to plus pi 2. Why? Because see here, this whole thing is the current carrying conductor, but the current I is flowing in the direction y to x. So to y to x means to the x it is entering, from y it is leaving. That's why I use the angle there as a minus pi 1. Okay, so minus pi 1 to pi 2 this is. So keeping mu naught by 4 pi outside and I by a also. So let apply only for this term. Okay, so that will be sin pi, and the limits are pi 1 to pi 2. Okay, go on writing the steps. Okay, so I hope you have written the last step properly. So is it visible? No. Okay, so mu naught upon 4 pi as it is I by a, and that limit value just we are substituting, and that is sin minus pi 1. Okay, so keeping these values as it is, it becomes sin pi 2 plus sin pi 1. Call this as equation number 3. So now you just assume that that conductor, whatever you have considered xy, that is infinitely long. If that is infinitely long, then pi 1 equal to pi 2 equal to 90 degree, and hence it is 1 and 1 2. So what is the value we got over there? Mu naught upon 4 pi I by a into 2. So this is the b value. Just again simplify. So b is equal to what we obtained, mu naught upon 2 pi a into I. Okay, so this is the value for magnetic field at a point on the straight conductor carrying current. Okay, so now you just can understand that this mu naught and 2 pi are the what? Mu naught by 2 pi is one constant. So can you write here as b is directly proportional to I by a. So the value of b depends on the values of I and a. Understood? I is current and a is the distance between the distance of p from the current carrying conductor. Understood? So this is the first value, or the equation we obtained from the first derivation. That is what? Magnetic field at a point due to a current carrying conductor. Understood? This is the first one. Okay, without wasting much time, let's go for the second derivation. So as I told you, what we considered in the second derivation, in the second derivation I have considered the circular coil. I have considered circular coil. Let's consider one circular coil or somewhat of this type. Okay, go on writing the derivations. Okay, so just consider a circular coil of radius a. Okay, so this is having the radius a. This is one circular coil having radius a. So in this circular coil, the current I is flowing in this direction, like this. Like this, current I is flowing. Okay. So again, here also we have to consider the point P. Here also we have to consider somewhere here consider a point P. Okay, so it is on the axis. It is, so if it is the center of the circular coil, so this is the what, this is A, this is what, radius of the circular coil is A. Okay, so this point P is at a distance x from the center, not from circumferences, it is from the center, and that is x. Okay, so here also now what we have to consider, we have to consider the current elements. Current elements, so here like this we will consider the current elements now. Okay, so this AB is one current element, and CD, two current elements we are considering. CD is also one current element. They are kept at the circumference of the circular coil. Okay, so each of them is having the length what, dl. Each of them is having the length dl. Okay, so now let's join the points from CD, also one line to P, and from AB also one line to P. Okay, so what this distance you can write? What is this distance? Because this is x, this is A. Circle, radius of the circle is what? A, and this is x. So can you write this distance? This distance from AB to P or CD to P, can you write it as root of a square plus x square? Yes, it is right. Understood. So only this much is representation, diagramical representation. So now let's write the magnetic field at P. Magnetic field at P due to the current element AB. Let's write that first. dB is equal to mu naught upon 4 pi ideal divided by ideal sine theta. Okay, and obviously the value of theta is 90, so it is 1. If you leave it also no problem. So a square plus x square is the distance here. Understood? R square. So according to Biot-Savart's law, what is the denominator over here? R square. So a square plus root of a square plus a square whole square. That's why a square plus x square I have written. Let's call it as equation number 1 now. Okay, so this is perpendicular. So from where, so this magnetic field whatever we have written, that is its direction is perpendicular to the line joining AB to P. Means from the center of AB I have drawn one line to P. So here this is what the current, this is the magnetic field due to the current element AB. Okay, so this magnetic field's direction is what? Perpendicular to the line joining AB. Line joining AB to P. So this magnetic field direction is like this, perpendicular to line joining P to center of AB. Let's consider this some one point. Okay, let ABCDE. Okay, E is the center point of AB. E is the center point of AB. So from the center point we have drawn one line to P. So to this line EP, the magnetic field is what? Perpendicular. Similarly, if you write the magnetic field at P due to CD, the same thing, but its direction is also perpendicular to the line joining center of CD to P. Let's call this as M. So PL and PM are what? PL is the direction of magnetic field at point P due to the current element AB, and PM is the direction of magnetic field due to the current element CD at P. Understood? So now here let consider this E is the center point of AB, and let F as the center point of CD. So from EPO, let consider the angle theta, and OPF, consider the angle theta. So but both of them angle is what? Same. So EPO is equal to FPO, and that is what? Theta only. Okay, EPO is equal to FPO. F and E are what? Center points of the current element, and that is theta only. Okay, so here you can write the components of magnetic field. Components of magnetic field, that is like this. This is dB cos theta, and this is dB cos theta. Okay, what is that? dB cos theta is perpendicular to the axis of the coil, due to the two opposite elements. Two opposite elements cancels each other. Hence, this dB cos theta is perpendicular to the axis of the coil. Understood? And the component of sin theta, dB sin theta, is along the axis. Hence, means here you are having two elements which are opposite to each other. So this dB cos theta are what? Perpendicular to the axis of the coil. And dB sin theta, dB cos theta is because of this, dB cos theta is because of this. Here also we get two dB sin thetas, one from the AB, one from the CD, but they are along the axis. Understood? So here the total magnetic field at point P, total means not only from AB, not only from CD, the entire coil, the total magnetic field at the point P due to the entire coil we have to write. That's why we are considering all these components and all. Okay, so the total magnetic field at a point P due to the entire coil can be written as B equal to 0 to 2 pi A, because entire coil, and that is dB sin theta. This is the what? Magnetic field component along the axis of the coil, and these are the magnetic field components perpendicular to the axis, and hence they are opposite to each other, they get cancels. So only dB sin theta is remaining, and 0 to 2 pi A, because it is from the whole entire coil. Okay, so already you know the value of dB. What is the value of dB? Mu naught upon 4 pi I dl divided by a square plus x square. Now here one more sin theta came here. Don't forget, this sin theta is not from the here. This is from here. Here we have not written sin theta in the initial, because that is already perpendicular, and that is 1. So here one sin theta we arised from this component of the magnetic field. Okay, now just go on solving this. 0 to 2 pi A is there. Mu naught upon 4 pi is obviously one constant. Okay, so can you write here it as sin theta value? Can you write here the sin theta value? Sin theta is nothing but what? Here sin theta is equal to opposite upon hypotenuse, A divided by this, a square plus x square raised to 1 by 2. So I dl a square plus x square, sin theta value is A, this is A, no, radius, A divided by square root of a square plus x square, a square plus x square raised to 1 by 2. So what it becomes? 0 to 2 pi A mu naught upon 4 pi I dl a divided by a square plus x square raised to 3 by 2. Okay na? So now apply the integration. Keeping mu naught by 4 pi outside, applying the integration, so it only becomes a square plus x square raised to 3 by 2. In the place of dl we have applied. Okay, and upper limit is 2 pi a and it is 0. 0, that term vanishes, so only thing remaining is 2 pi a. Okay, now just adjust the terms. So what you get b as 4 pi get cancels, a becomes a square, 2 2s are 2 2s are, and like it is, that whole term remains is mu naught, and I is remaining, a become a square. Okay, divided by 2 into pi get cancels already, a square plus x square raised to 3 by 2. Call it as equation number 2. Okay, so now if this coil has n number of turns, if coil has n number of turns, then the same equation we can write. I'll write here, see, same we can write it here as mu naught n I a square, because it is having n number of turns. Okay, and 2 into a square plus x square raised to 3 by 2. Okay, so if at the center of the coil, x, what is x value at the center of the coil? See here, what is x value? No, na, it is no, we are not having x value here. So at the center of the coil, x is equal to 0. So if x is equal to 0, then what is the value of b? Mu naught n I. X is equal to 0 means substitute x equal to 0 here. So a cube came. Okay na? So a square, a cube cancelled. So here 1a is remaining. 2a. Okay. This is the general equation. And this is the first case when x is equal to 0. So in the second case, if x is very much greater than a, if x is very much greater than, means this point P is very much away from the center. So a is less as compared to x. No, x is very much greater than a. So in that case, the b value stands as mu naught n I. Okay, b equal to mu naught n I a square divided by 2x cube. So this is when x is very much greater than a. This is x is equal to 0. But the general magnetic field value for a circular coil carrying current is this: mu naught into ni a square whole divided by 2a square plus x square raised to 3 by 2. Okay, I think no need to repeat all the things once again, because it is a derivation. You can revise it by revising the video. Okay, so 2 derivations we have completed today. This also completed. Okay, very important derivations are there. They may ask it for 5 marks. So before giving the notes from my side, you keep it as your own notes only. Okay, after at the end of the chapter I'll give the notes, but till that you should have a rough notes with you. Understood? Which is own made. Okay, I hope you understood the derivations. So in any step of the derivation, in these 2 derivations, at any step, at any single step, if you face any problem, just call me or just ask me. Because don't be with the queries. Make these derivations perfect today itself. In the next class, one more derivation I'll tell, and we'll talk about the Helmholtz galvanometer in the next class. Okay, but before that, just make these 2 derivations perfect. Okay, thank you.